Hello, in today's lecture, we are going to study a free particle on a circle. So, in quantum mechanics, we basically try some different sort of uh, different potentials. And one of those important case I'm considering today, and let us consider a particle which is constrained. Let us consider a particle which is constrained to move on a circle of, let us say, some circumference I'll give of some circumference L. That is, uh, if I say that my circle is having this kind of, this is the circle, and okay, and if this is a circle, and let's say if x defines the length here, then x is constrained between 0 to L. X is constrained between 0 to L. And what is the quality of circle? That if I've started from here, if it is if I make a complete circle, I'll end here. Okay. So additionally, we should remember that x should be equals to what? X plus L, or what you can say that any quantity, if I'm trying to write, I should have a periodicity. I should have a periodicity. So the wave function must follow this periodicity, that is psi should be equals to psi of x plus L. Okay, psi must be following this kind of periodicity. Okay, so I must satisfy this periodic condition. Okay, because you know that any of these coordinates, let's say I start from 0, and if I complete it and complete back, I have covered complete circumference, which is length L. So 0 is equal to 0 plus L here. Okay, so you are at the same point. So your quantity psi must be defined in such a way that psi 0 should be equals to what? Psi L. So this is inherent. So I don't think it needs much explanation. Okay. Another thing that one can clearly see from here, that not only psi is periodic, but rather all its higher order derivatives also are periodic. Because if you differentiate, it is quite understood that if not only psi is periodic, but also the derivatives, all of its derivatives rather, all of its derivatives are periodic. So these are important observations that I have already written. Okay, so this is good observation that you might have seen. Okay. So it is understood, I hope. Okay. Now, we have already assumed another thing, that our particle is free. Now, what do you mean by free particle? It implies that my potential is equal to 0 when I'm moving on the circle. That is, when my particle is constrained on a circle, it feels no such potential. That is, the potential is simply 0. And so therefore, the time independent Schrodinger equation will take this form: minus hk square upon twice m del square psi upon del x square is equal to E psi. Now question arises that what should be the sign of E, whether E is less than 0, whether E is greater than or equal to 0. Okay, so for this, let us try to resolve this query first, and then we'll move ahead. So let us first resolve the query that whether E is less than 0 or E is greater than equal to 0. So what I'll do, I'll simply multiply this particular equation. So let me write this equation number 1. So I'll multiply this equation 1 by psi star and try to integrate from 0 to L. Okay. So I hope once I do this, then you will be able to understand why am I doing this. So psi star d square psi upon dx square. So sorry. From integral from 0 to L must be equal to E times integration from 0 to L psi star psi dx. Really, psi star psi dx from 0 to L, it should be equals to what, 1. And so it implies that E is equals to minus h ket square upon twice m integration from 0 to L psi star d square psi upon dx square dx. And if I play a certain way, a certain mathematical trick, so I can write this with this thing as h ket square upon twice m integration from 0 to L, and then I'll simply write it as d by dx psi star d psi by dx. And what additional thing I'm going to get from here, because I only want this thing, so I'll subtract it from d psi star upon dx into d psi upon dx. Okay, and I know that this thing can be written as E, now can be written as simply minus h ket square upon twice m. You have this psi star d psi upon dx from 0 to L. Okay, and then plus h ket square upon twice m integration from 0 to L, and this is d psi upon dx mod whole square. I hope it is clear. Okay, I'm getting a little bit of problem here, lack of space, I think. Okay, so now E is equals to what? So I have to place upper limit and lower limit here. So I'll place upper and lower limit. So E is equal to what? E is equal to minus h ket square upon twice m, making the bigger bracket. And now I'll simply write psi star d psi upon dx at x equal to L minus psi star into d psi upon dx at x equal to 0, and then plus h ket square upon twice m integration from 0 to L d psi upon dx mod whole square dx. Okay, so overall this E is equals to what? E is equals to, okay, so this condition, just remember this condition. I already have told you that psi at 0 would be equals to what? Psi at L, and psi dash at 0 would be equals to what? Psi dash at L. This is the condition that we wrote initially. So this particular first bracket would become 0, and energy could be written as simply h ket square upon twice m integral from 0 to L d psi upon dx mod whole square dx. And clearly this should be greater than equal to 0. So this sums up our case that this energy that we are writing here, E, must be greater than equal to 0. So I'm here writing E must be greater than equal to 0. E cannot be less than 0. Okay. So this is clear. Now, Now let us, having done this thing, I'll do this thing is a standard thing, d square upon dx square plus d square psi upon dx square plus 2me upon h ket square psi is equal to 0. And we write this as k square. So your k square is equal to what? K square is simply your 2me upon h ket square. And you know that e is greater than or equal to 0. So you can take that, you can take this, I mean, you can take this consideration that k square is equal to 2me upon h ket square. And it gives us a result that d square psi upon dx square is k square psi equal to 0. Now the solutions for this particular equation would be in sines and cosines, but I'm writing for purposefully in terms of e to the power iota kx, and obviously you can obviously write e to the power iota kx as uh, obviously, you know that the solutions will get in the form of sine kx and cos kx. Rather, let us use a little bit more general approach. So one thing is clear that psi x must be some constant times, e to the power iota kx. I'm not writing, not writing normalization constant and all. Right now, I'm just writing that psi x must be of the form of e to the power iota kx. One important thing that you can see here is that I'm writing it here. One important thing here, we can see that this is a, I'm writing it here. Okay. This particular thing, I'm writing it here, that it is a momentum eigenstate. This is a momentum eigenstate. Okay, because what is momentum? Momentum is minus iota h ket del by del x. So if I differentiate, I will simply get uh, I will simply get what? I will simply get h ket k and e to the power iota kx. So clearly, this wave function represented by e to the power iota kx is a momentum eigenstate. So this I have already written so that you remember. And also we know that from periodic condition, we know that psi x must be equal to what? Must be equal to psi of x plus L. And if psi of x is equal to psi of x plus L, it implies what? E to the power iota kx must be equals to e to the power iota k of x plus L. And which requires what? It requires that e to the power iota kl must be equal to 1, and which requires that your kl must be 2n pi. Okay? Or simply k as a function of n, like this quantum number will be 2n pi upon n. Here n belongs to set of integers. Okay? So far we have not done anything very dramatic. We have just used the Schrodinger equation, and I have just proven that E must be greater than or equal to 0. And second thing I have done is I have utilized my periodic condition and written that the allowed values for this K must be some discrete values. These are 2n pi upon L. Okay, so now I can write my what you can say Schrodinger equation. The solution for the Schrodinger equation psi a, I'll write simply as n some constant e to the power iota knx. And if I want to determine my normalization constant n, I have to do this psi n star psi n dx integration from 0 to L equals to 1, and I will get that n is equal to 1 upon root over n. What does it imply? It implies that my psi n is equals to 1 over root over L exponential iota 2n pi x upon. So this is my wave function corresponding to the problem free particle on a circle. Now, what do you think the energy would be? So you know energy is equal to what? Energy is simply h ket square k square. So instead k we have kn square. We have only some discrete allowed values upon twice n. And it is equals to what? It is equals to h ket square 4 n square pi square upon 2m L square. So we'll get what? We'll get 2 pi square h ket square n square upon ml square. So these are the allowed energy states. In fact, you can know that since n can go towards infinity, so there are infinitely many allowed energy eigenstates. Okay. One important. So this sums up your discussion on free particle on a circle. So we have derived what? We have derived the wave function, and we have also derived the energy eigenstates. In the next session, we are going to start with the same topic, a little bit of qualitative discussions, and a new topic called as the symmetry potential. Till then, take care. Bye-bye.